I guess I'm going to repeat myself because I forgot that I wasn't recording. Normally, I end up doing a lot of little in-class demos to show you guys stuff that we already know intuitively. This by far is the most intuitive section of our class, where again, I'm not going to tell you something you don't know. I'm just going to tell you why, and I'm going to tell you how. And we're going to be able to start doing some quantitative on top of qualitative reasoning for the phenomenon we know about gases. Again, this is a one chapter, one test. So this is our last hurrah to get a really good score before we head into the final, sort of pad our grade up just a little bit more. Normally I do a bunch of demos. I obviously can't do them for you. I don't have the equipment, and it would look really weird on the screen anyway, even if I could have stolen it from work and performed the test here. So I'll probably, this will probably be a little drier than a normal session, and I may start into some problem solving before the end of the day so we can get a lot of practice. Let's see, is there anything else I needed to mention? I think that's it for now. Oh, and then after the lecture, if people want to bone up on their math, I can do that too. Because really, once we have a few concepts down, it really is just math and hopefully simple math. So I'm going to do this for you. We're going to be talking for the next 2 days about ideal gases. And before I even talk about them, I'm going to give you guys everything you need to know in one spot. And the things you need to know are that PV equals nRT. You need to know that P1 V1 over T1 equals P2 V2 over T2. You need to know that 760 millimeters of mercury is equal to 1 atmosphere, and that the total pressure is equal to the sum of all the other pressures. These 4 things right here will get you through every problem that I'm going to give you on the exam. All 4 equations, all in one spot. We'll go ahead and define some of these here in just a moment, but I wanted to make sure that we had just a single spot that we could go to in our notes when we're doing the homework problems and stuff like that. You pull up this one spot, you have everything you need one place. Now, I'll go ahead and verbally just tell you guys this, but we'll define them a little bit later. I'll use my mouse here. Hopefully it's intuitive. We're talking about gases. And if we're talking about gases, what do you think V might stand for?
Volume.
Volume. P?
Pressure.
T?
Temperature.
Temperature. So we see that echoed over here in the P1 V1 over T1 equation. So we already know a lot of the symbols here. This N is actually the number of moles of gas, or the amount. And R is something that we'll call the gas constant, and I'll be defining that a little bit later. And so we'll have the bigger definitions a little bit later. And the only other thing here is the 1 and the 2 just means they're going from one set of conditions to a second set of conditions. And we'll do a lot of problems about that. So I won't put the definitions here. I'll put them later on in the body of the text, but just keep our equations up here as frame of references. Okay, so what do we know about gases so far? What do we already intuitively know about gases?
They fulfill the octet rule.
That would be a true statement, because the gases are, well, no, I don't want to say that, and I'll show you why in a second. The gases you're thinking of, you're not wrong in that. You're thinking of things like carbon dioxide or even water vapor or sulfur dioxide gases, And we use those as examples when we were talking about octets. So you're not wrong in that, but I want to steer away from that because not all gases have to have octets. You'll see what I mean in a second. What I mean is physically here. What do we already know about gases? If we set the way, way back machine when we were talking about.
They fill up empty spaces.
Yeah, right. They fill empty spaces. Are they dense or not?
Low density.
Low density.
Low density. We can see through them. They fill empty spaces. Do they mix really well or not? Just think intuitively.
Yeah.
Yes.
Yes.
You have to, right? We talk about air being that homogeneous mixture of oxygen and nitrogen. Yeah, they have to be very mixable.
Compressible.
And compressible. I was just about ready to head there. Thank you. Right? So we have compressed gas cylinders. We can take those, unlike solids and liquids, we can compress gases. And mostly because they are low density. And they will fill their spaces. Remember when we talked about vapor pressure and I said, if I spilled a bottle of perfume on the table, eventually that perfume would fill the room. Everyone would smell the perfume. And that's because all of those gas molecules of the perfume are getting up and going into whatever empty space they see, which is essentially the room. The room is a bunch of empty space to them. And they're going to fill that room, every corner, as far as they can go. So we already know this stuff about the gases. But let's talk about what makes these gases ideal. What does it mean to be an ideal gas? So what does it mean to be an ideal gas? Well, the simple answer is it behaves. It is predictable. So what do I mean by it behaves or it's predictable? If I ask you, I have a balloon and I heat up that balloon, is it going to get bigger or smaller?
Bigger.
Now, is
Like
that
a hot air balloon?
Right, hot air balloons. You get that hot gas there, and it expands, right? So if I get it hot, it expands. If I cool it down, it
Shrinks.
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 Smaller.
Right?
Yeah.
We know this. If I have a sealed container, say like a spray can of paint or something like that, and I get it hot, will the pressure inside that can go up or go down?
Up.
That's why we don't store those things in hot places, right? That pressure goes up, the can explodes.
Yeah.
Presumably. Okay, so we already have an intuition about how gases behave. And so all the gases we've been thinking about already do what we want them to do. Now, there are gases that won't behave or can be put into conditions where they won't behave, but we're not going to talk about those. All right, we're going to talk about ideal gases, and it means we can predict it. So, you know, i.e., you heat up a gas, it expands, cool it down, it shrinks, right? We already know this. The stuff that we intuitively know, that is an ideal gas. It behaves. So what conditions will actually make a gas ideal? So what physical conditions make a gas behave? Make it ideal.
Low temperature, high
It turns
pressure.
out
Oh, sorry.
Temperature and pressure. Yeah.
Temperature and pressure are definitely the things. Reagan, you just had it backward is all. What I'm going to put down here is relatively high temperature and relatively low pressure. Now the temperature thing, if you think about that one, it's probably a little more intuitive. The hotter you get a gas, the more you let it move around, the more you let it do whatever it wants to do. If you continue to cool and cool and cool a gas, and you make it slower and slower and slower, eventually it will condense. We know that from water vapor. You get that hot, humid air, it hits a cold surface, slows down, sticks, right? So when we think about relatively high temperature, I put that relative because who said the octet? Who's the person that said octet?
Me, Angel.
Oh, Angel.
Angel, yeah. So you were thinking about all of those non-metals that we look at as gases, fluorine, chlorine, sulfur dioxide, carbon dioxide. Now, those are all floating around right now because room temperature, as we're sitting here right now, is relatively high for them. Now, they can get pretty darn cold before they actually stop behaving ideally. Carbon dioxide can get pretty cold before it starts not behaving like we want it to. And remember, eventually you can get it cold enough. You can make liquid carbon dioxide. You can even get it down to be a solid. But the further you get away from that ideal, the more, or that relatively high temperature, the more that it'll stop behaving. The gases that we talk about here, and the only ones we will, are the ones that will behave, the ones that we're familiar with: helium, hydrogen, carbon dioxide, water vapor, you name it. Because at the temperatures that you and I exist, the temperatures you and I feel, that temperature is high enough for that thing to be behaving. So relatively high temp, I say the relative because there are things that can be gases and can behave, period, octets or no. You just have to get them hot enough. You can make gold behave like an ideal gas. You just have to heat it up a whole hell of a lot. I know it sounds weird. You have solid gold. How is that going to be a gas, and how does that even behave? Well, in my graduate work, I actually worked on depositing thin layers of gold onto glass slides so I could do some reactions at a two-dimensional surface. I did that by taking these glass slides and I put them into a chamber, and I would take lasers and I would essentially just beat it up with so much energy that it would sublime straight into the gaseous state. And once it was a gas, it moved around, filled the chamber. Man, the inside of that chamber was beautiful. It was all coated in glass or gold, except for where the glass slide was. There was just a piece of iron right behind it. So when we say relatively high temp, it is molecule dependent. You can make anything behave. You just have to get it hot enough. You can do the same thing with pressure, right? So relatively high temp, get it hot enough, everything will behave. Get it hot enough, it'll behave.
Forrest, can you define, I guess, behave? Does that mean it's predictable?
Yeah, predictable. Yeah, exactly. Make it behave. It's predictable.
Okay.
Yeah. So when you say behave, predictable. So we heat it up, it expands, and it expands how we think it would. If I get it twice as hot, it will become twice as big. Basically, that's what it boils down to. If I make it twice as hot and it doesn't get twice as big, well, then I'm probably not in the right conditions for the gas to behave. You and I, for this class and for our lives, I've seen things do non-ideal behavior only once, and it was in an experiment that we had to do just to prove that, yeah, you can mess with gases enough. Never seen it since. You and I, all the gases we care about will be ones that behave. we will be able to predict what they do. Everything will behave. Now, the low pressure is another situation. Low pressure, if you think about it, pressure is caused by something pushing on you, and we'll talk about that in a moment. The more pressure you put on a gas, the more you kind of make it interact with each other, the more you make them see each other, the more they don't like to do what you ask them to do. So the easiest way to make something behave is take away the pressure. Take away the people around them and let them have their space, and they will go ahead and do what you want them to do. Now, again, the relatively low, this is because it's all gas dependent. So the relative is gas dependent. And heat it up and it turned into a gas, floated around a little bit, floated up. But for that brief instant, it was at the perfect temperature to go ahead and do exactly what we wanted to do. And we actually didn't have to get it that hot to do it. I mean, I was making it really hot just to make it go faster. But iodine, you don't have to heat it up very much, and it will actually turn into a gas and it'll do its thing. So everything is relevant, relative for the gas that we're talking about. So for it to be ideal, it's high.
Scroll, I'm sorry, before you keep scrolling down, I missed something under it behaves, it is predictable. You said heat up a gas, it expands, and then there was something else below it, but I don't have that. Oh, heat up a gas, cool it down, and it will shrink. Okay, so that's.
Yeah, I wrote that because you said that.
Oh, good, thank you. Cool it down, and it will shrink. I just got it wrong. Thanks, okay, I'm cool.
That's right. So when we're looking at this, and I just wanted to point out, we're talking about high temperature and low pressure relative, and this relative I'm going to make permanent for our class. Essentially, no matter what you think of the number that you get, unless you just is really, really wrong, don't be shocked, because I've already looked up to make sure that the gas would behave at the temperatures and pressures that we're dealing with. So yeah, even if you're like, oh, whoa, that's really cold, or wow, that's pretty high pressure. Well, for that gas, it was okay. Pretty much, as long as you stay around under 10 or 15 atmospheres, most gases that you and I know, they'll be all right. You start getting into 20 and 30 atmospheres, things get a little weird. Now, leave me alone, cat. All right. Let's take a look at this idea here of pressure. It's something I should define. Temperature, we already defined the average kinetic energy of the molecules of the system. But what is pressure? What is pressure? Aside from the thing you feel every time that I ask you guys a question. Anybody here in physics or taking a physics?
Resistance.
The force?
Yeah, I was gonna say the force of.
The force of something?
Pressure is a force. So pressure is a force over an area. And in fact, if we rack our brains, we might know this guy. What's PSI? I heard no, yeah, what was that?
I was thinking of my tires, so it's.
Per square inch.
Yes, I heard someone whisper it. It's pounds per, and per means divide, square inch. There you have a force over an area. Pounds per square inch. And that's where we get the term PSI. So a pressure is a force over an area. If you want to increase the pressure of something, you increase the force. or you get rid of the area, you decrease the area, you apply the same force over a smaller area. Now, for anybody who's watched any of those cool documentaries about like different cultures, you might have run across something where there are these people that lay down on beds of nails. And you may have noticed that you almost never see them when they're getting onto the bed of nails, and maybe not even when they're getting off. You just see them laying on the bed of nails and think, that seems like it shouldn't be able to be done. Because I'm pretty sure many of us have stepped on a nail and that nail's gone straight into your foot. So you may be asking yourself, how is it that all these nails aren't just like piercing this person? Well,
Can you repeat that again, please?
I didn't hear him after well.
Me too.
I think he lost.
Frozen.
Oh, he's still on.
Maybe he's trying the experiment and it really hurt.
It might just be his connection and he's frozen.
I think his connection is pretty bad and we can't hear him anymore.
Reagan, stop it.
Ah,
There he goes.
He left. He's gone.
Daisy's
Because
now the
Daisy
host.
is the host.
Take us through it, Daisy. Daisy, since you're the host, can we talk about my test?
What are we going to learn about today?
Everybody gets an A.
Did he talk about the test before I went on?
No, it hasn't been met.
Okay, because I had a hard time logging on. Took me a while.
Right, it is still recording.
Every time he says pressure, I think of that Billy Joel
are we
song.
back in?
yeah, you're here.
Woo! I'm the host now. Who's the temper?
Back.
You took it from
Who's
Daisy.
the one was gone?
Daisy.
Reagan.
No, I wasn't. Daisy was the host. I was just the MC.
Nice. You ever wonder like how they spell MC?
EMCEE.
Right? Isn't that weird that you don't just say MC? You can actually spell out that word. It's kind of wild. So hey, since I don't even know where I lost you guys, did we get to the point where if the guy sits up too fast, he gets a nail up the nether regions?
You just
No,
finished
no,
explaining
no.
TSI.
I just got finished with what?
TSI.
Well, you were talking about if we step on if somebody didn't get all those nails or something, we stepped on a nail. I don't know.
Okay. So what I was saying is the person who lays down on the bed of nails is unharmed.
Cutting out again.
But if you, with a singular nail, you have 150 pounds spread out over one little nail point, but that person laying on the bed of nails has essentially taken that 150 pounds and distributed it over, say, 1,000 nails. And so there's 1,000 times less pressure on any one point of that person. So that's why there's not enough pressure to actually force through and break the skin on the person and impale them. Now, if you've been really good and been able to see the beginning and the end of all this, there's usually a lot of people helping this person on and off that bed of nails, because you can imagine trying to lower yourself all at the same time onto those nails such that you don't, sit first and then watch them go bad places. So it's all about, in that place, either increase pressure or vice versa. But this pressure, force over whatever area you have. And when we talk about that, for gases, where does this force come from? So for gases,
You're not broadcasting. Your screen's not
Oh,
up.
am I not? What?
Yeah, your screen's not up. We can hear you, but you're.
Oh, I see. Thank you. Thank you. Share screen. I'm like,
Yeah.
where's my participant list? Because when it booted me out of Zoom, it stopped sharing. All right. Thank you. Technology is great when it works. When it doesn't, it really sucks. Where does this pressure come from? Now, even though we can't see them, we can see their effect. I was actually just remarking to my kid last week when he had all those big winds come through. He's like, how come the trees are moving? And I was like, oh man, you asked the right person. And so he got more than he bargained for as far as the explanation. Most of you would probably go like, it's the wind. Oh, not in my house. And he's like, well, son, you see, the wind is made up of billions upon billions of tiny particles of air.
Wicked.
And technically, these molecules that you cannot see do take up space and do actually have mass. And as they are moving through the tree, they're hitting that tree. And every time they hit that tree, they're pushing that tree. And so even though you can't see those tiny little molecules, you can see their effect. And I could tell in his look, he's like, oh, really, Dad? But he said, cool. But I know what he was thinking. Didn't you just said the wind? But when I stop and I think about that explanation, there was a lot wrapped up in there that I hope you guys also see. And that is that even though we can't see these gas molecules, we do know that they have mass. We've calculated their molar masses. And those masses are flying around at a certain speed. And if anything, no matter what it is moving and hits something, it's going to give its force, it's going to slam into it and cause that pressure. So for gases, where does this pressure come from? Gas molecules hit stuff. And when they hit stuff, that is the force. So even though we can't see them, we can feel their effect. Now, gas molecules hitting stuff, it is a force over an area. Now, as we look at this force and we look at the area, I do want to point out that this right here is going to now get us back to, is there like another chat thing? What happened? I saw a flash. Made me think of Lion King. Oh, balls of gas. I was actually, April, I was, for those of us of a certain age, I was remembering Carl Sagan. So put that in your hat. We're going to, at this point, start learning about the third thing I wrote up there, and that is this 760 millimeters is equal to 1 atmosphere. Because while most of us grew up here in the States hearing about this PSI thing, and we just sort of take it as it's a number, we inflate our tires to it, I don't really know what it means, I just know I got to get there. Up until very recently, or relatively recently, we really didn't know what pressure was. We had no way of quantifying it. And in fact, this is where it just blows my mind. When we talked about temperature, and I said, look, we haven't really known about temperature except for like, what, a couple hundred years maybe? It's only a little bit longer that we've actually understood pressure. And so let's talk about that pressure. So we know where it comes from. Gas molecules hit stuff, but how do we define it? Oops. But how is it defined? Okay. When we talked about temperature, we had the Kelvin scale go down to 0, nothing's moving except for electrons whizzing around the nucleus. Or if we're talking about Celsius, it's where water freezes and boils and stuff like that. So we had a benchmark. We had a place where it's defined. Now, it turns out, how is it defined? Okay, here we go. It is defined by this guy. Is it 2 C's or 1 C for Torricelli? I think it's 1. Torricelli was an Italian guy in the year 1643. He plays with mercury. Specifically, what he does is he takes, ooh, I might be able to do a cool shape here, hold on. Is he takes, no, I don't like that. Get rid of that, I'll just draw it. He takes a big pool of mercury. He takes a test tube full of mercury and he upends it into this pool. Now, if you've ever done this, you know what I'm talking about. You have taken a cup full of water, stuck it upside down inside of a tub of water, and you notice that the water inside of your cup does not fall out. Out of curiosity, has anyone ever done something like that in just their daily life?
Yes.
Yeah, and it's a weird phenomenon. You're like, wait, why isn't it falling out? So let me ask a question to the class. Can we agree that all of this mercury in here, right, so we got a bunch of mercury, would love to fall out of that tube, would love to have gravity pull it out?
Yes.
Yes.
Thank you. Right, so the mercury wants to go down, you know, gravity. Oops, gravity pulls it down. Okay, so we have all this mercury here. And so if it wants to come down, then this level here would want to go up, yes?
Yes.
Okay. But it doesn't. Now, if any of my physics people would have spoken up there, I would have said, if it wants to go up, but it is not, then that means what? Something is not letting it.
Pressure.
Now, the pressure. Now, the pressure of what?
Oxygen?
I heard someone say pressure. Say it again.
I don't know. Oxygen? Like the air?
The air itself actually is what I was going to get at. Is if there was a force going up, right? This would go up. There must be some sort of force. Actually, I'm going to put it on. Well, I'll put it on this side. There must be some sort of force pushing it back down. And the air keeps pushing it down. If one thing wants to move and it ain't moving, it's because it is pushing back. It is saying, no, you can't do this. The classic physics problem is you go up next to a wall and you push on it and the wall doesn't move. Why? The wall is pushing back at you and saying, no. For each action, there's an equal and opposite reaction. So here we have this sealed tube of mercury. The mercury wants to fall out. It wants to get pulled down by gravity. It wants to go into the pool. But if it were to do so, the level of the pool would rise. It does not. And that's because there's a force on the outside pushing it down. Now, Torricelli was working with this, and he kept making various different sizes of tubes and making them longer and longer and longer. And what he noticed is, as long as the height of that tube was less than or equal to 760 millimeters tall, the air pressure would win. As soon as he made it taller than 760, say 800 or 900, the mercury inside would fall down until it stayed at 760 millimeters tall. So if it were above that height, it would fall down until it reached there. If it were below, it would just stay where it was. The air is not going to push it back up until it reaches there. But as long as this height difference right here was 760 millimeters tall, that was 1 atmosphere. And that's where we get this equating. It seems a little weird that we have this 760 millimeters of mercury, a length scale, somehow equaling 1 atmosphere. So what he did by playing around, experimenting around, figuring out these different heights, and the widths didn't matter, by the way. It was all about the height. By making it, he zeroed in on this mystical, magical 760 millimeters would be 1 atmosphere's worth of pressure. Now, this is where it gets kind of fun. So far, so good. We now have a way of measuring pressure. So, weather person says, the mercury is falling. Has anyone heard this term, mercury falling or mercury rising? Does anyone listen to the weather person anymore? No, we just go online and,
I think
No,
it's
it
like
used to
the
be a
only
term.
job that you can get your job wrong like 90% of the time and still keep your job.
that or mine, you know.
You mean the temperature is rising or going down?
So when the mercury is rising or falling, a lot of people think that the weather person is saying, hey, it's getting hotter or colder. That is true, but he's not looking at the mercury in the thermometer, looking at the mercury in this apparatus right here called a barometer. So this is a barometer. And bar means pressure. It's a measurement of the pressure. When it says the mercury is falling, it says the pressure is dropping. Now, for anybody who's been in the Midwest, they'll know what I'm talking about next, especially if the pressure drops incredibly quickly, they know there's a problem coming. Usually something bad, and the temperature follows suit. The pressure is dropping, and the temperature follows. Now you can imagine if the air pressure around becomes less, as those blue arrows right there become less, and the force pushing back on the pool is less, gravity can win, and we can start flowing up the pool, which means this height here drops down. When there's less pressure outside, the height of the column drops down. When there's more pressure, when the mercury is rising, a high pressure system coming in, you will end up with higher temperatures as well. Now the key of this here actually is this sealing of the tube on top. Because if we didn't seal that, then, what's this, and baseball players, I don't get it, Nathan. When we look at this, it is important that it's sealed on the top. And that's because right now we have a whole bunch of air on the outside here that is pushing down, and there's basically no air up here to help. If we suddenly poked a hole in the top Air would rush in, push down just like all the other air out. Gravity wins. Everyone is liquid level height. So it's important that that's a sealed tube. Now, you guys have actually done this. Everyone has done this. If you haven't done it, you haven't lived. You're a kid, you're drinking a soda, you put the straw in the soda, you put your finger on the top, you pull it out, and magic. The liquid does not fall out, right? Do not raise your hand if you haven't done it. Just silently weep and then quickly go do it so that you can be happy again. So.
Friends don't use straws anymore. I'm just kidding.
You don't use straws? Oh dear. So the weatherverse says, so the mercury, what they're really talking about is the pressure. That's what they're really talking about. Temperature will follow. And, you know, your own daily life. Also, think about your finger on the top of a straw. Oops, that's a weird W. I'll see if I can draw a little picture for the people who haven't done it. All right, here we go. And then I'm going to draw a finger here. Put a little nail right there. Put a little knuckle. I don't know. No, there we go. And we're going to put our finger onto that, and we'll notice that we have some liquid in here. Just won't fall out. All right, liquid does not fall out. Can we agree that gravity is pulling it down?
Yes.
Yeah. So why doesn't it fall?
You put pressure against it.
Air pushing up. Okay, now that might be like a, well, duh, and it might be a, wait, what? Air pushes up? Yes. Air molecules are whizzing around in every direction possible. That includes left, right, down, and up. So these gas molecules are whizzing around in all directions at all times. And so, yeah, the air is pushing up against it. And of course, you also have surface tension where that liquid water doesn't want to let go of its buddies and just seep out the sides. So you have a couple of forces there to your advantage. Now, how do you make it fall? You just take your finger off, and then gas molecules at the top and the bottom are pushing. They negate each other. Gravity wins. Pro tip, gravity always wins. So this pressure of the air on the mercury gives us a sense of measurement of the pressure, a sense of the force that is happening there. So now we know what pressure is. We already knew what volume was, and we knew what temperature was. Now, what I want to do is talk about what behaviors, before we get into the other parts of the gas law, what behaviors does an ideal gas exhibit? Okay, so what I'm going to give you are the highlights of essentially the kinetic molecular theory of gases. So highlights of the kinetic molecular theory of gases. So I'm going to highlight some of the things that, that you have to have for this gas behaving ideal, and what is it going to look like if it's behaving ideally. Okay, everything I'm going to say is intuitive perhaps, but needs to be said. One, gases are mostly empty space. Now that should be kind of a duh. You know, we're looking out and we can see for miles through this gas, but it needs to be said that they are mostly empty space. Because what does that mean? They don't see each other. Which means they can do whatever they want. Nobody's going to tell on them. No one's going to make them behave. They do behave. No one's going to make them follow any other rules except for the rules they want to. Gases are mostly empty space. They have no affinity for their container nor each other. And what does that mean? It means that if they ever hit something, they don't stick. If they ever happen to see one another and bounce into each other, they'll just bounce off. They won't stick to it. So they have no affinity for their container nor each other. They will not stick to it. Now that's good, because if it did stick to it, it would cease to be a gas. Think about your cold soda on a hot day, those water molecules in the air sticking to that side of that glass. Yeah, they're no longer gas anymore. They're droplets. Gases are mostly empty space. They don't see each other. If they do, they don't care. And if they hit something, they don't care. All collisions are completely elastic. So what does that mean to be completely elastic? What do you think of when you think of elastic?
Stretchy?
Tendons.
Stretchy. What is stretchy?
Malleable?
Rubber
I was
band.
thinking of rubber.
Yeah, I was gonna say a rubber
yeah.
band. I don't know.
Yeah, no, exactly. Again, this whole section is about you guys just using your intuition. If you're thinking more than half a second, you're thinking too long. All collisions are completely elastic. Think rubber band. It comes back to its original shape. Okay, so all collisions are completely elastic. It comes back to its original shape. What this really means is they do not lose energy.
What do you mean by collisions, though? Like just gases like hitting each other?
Hitting the walls, right? They do not lose energy when they hit stuff. Okay, so that was you, right, April?
Yeah.
So yeah, it's really weird. Again, you know, like I said, my kid's gonna grow up like going like, man, why do I even ask questions anymore? Because I don't need the full scientific explanation. Okay, what I want you to do right now, April, is I want you to wave your hand around back and forth. Do you feel much on your hand?
No.
Are you waving?
No, just like
You
the
know-
wind from the air.
Now what I want you to do is drive down the highway at 70 miles an hour and stick your hand out. You feel it now?
Yeah.
Yeah. Why? Because you have all of those gas molecules that you're just like wading through like a bull in a china closet. You have all of those air molecules hitting your hand. And that hitting your hand creates a force on your hand. Now let's go back to when we were children and we loved this. We'd stick our hand out the window, and instead of opening our hand perpendicular, where we just like rake our hand all the way back and nearly snap it off, we stuck our hand into the wind, and we did a cool little wave thing, right? And you could feel the pressure on your hand, pushing it up and down depending upon how you moved your hand, because you would change the area over which those gas molecules were hitting you. So you would change the pressure you felt. It is weird sometimes for us to think about the fact that we are sitting here right now, wherever we are, and there are just stupid amounts of gas molecules right now pelting our bodies, hitting us, bouncing off, and hitting us and bouncing off. And they're constantly doing this all the time. If we were in class right now, I actually have a 15-pound metal rod that is 1 square inch on one end. And I would walk over to some people and I would stick it on their foot to let them know what 1 atmosphere actually feels like. It blows your mind. It's easy. If you have ever dived to the bottom of like a deep end of a swimming pool, okay, so like 10, 12, maybe even 14 feet. I want you to think about that if you've ever done that. You're at the bottom of that pool and you feel like, man, there's a lot of pressure on me. That's only about 1/3 of an atmosphere. That's only about 1/3 of an atmosphere in your body. Now, right now, as we're sitting here, we actually have an entire atmosphere's worth of pressure on our body. So what is the difference between now and at the bottom of the swimming pool? Give me that, Batman.
Pressure.
No, we have the pressure, right? I'm saying right now, who's just chatting instead of talking?
Emily said we're used to it.
Yes, we are used to it. Very good, Emily. Here's the deal. We are born into this world with that pressure upon us, period. We already know what 1 atmosphere feels like, so we zero it out. Our bodies just go like, yeah, that's normal, okay? So I also liken it to this. You know, you're a young child, you're having a hard time going to sleep. Grandma walks in, just starts rubbing your head and rubbing your head and rubbing your head, and everything's great. Everything's great until she stops. And that's when we actually realize Grandma's been rubbing our head this whole time, because we got used to the feel of the hand rubbing over our head. And we only noticed it when it stopped because we got used to it. Now, that's the same thing with the pressure that you and I feel right now, is we have all of these gas molecules that have been constantly hitting us our entire lives. We just account that to background noise. We don't even notice it anymore because there it is. When do we notice it? When there's a change. When we're going 70 miles an hour down the highway and we stick our hand out and now we have a whole lot more pressure on our body, we can feel that. But until that point, we're just walking around doing nothing. But these gas molecules are constantly hitting us, constantly hitting the walls, giving the force and then rebounding, not losing any of their energy. And that's an important thing here. Even though it might seem kind of intuitive, it's important that they don't lose their energy. Because remember, temperature is the average kinetic energy of the molecule. So if you're talking about the gases in your room right now, the air in your room, and they're constantly hitting the walls, your computer, your desk, your chair, the floor, you, if every time they hit something, they rebounded a little bit slower. Think about billiard balls on a pool table. Eventually they slow down and stop. Okay, what if our air molecules did the same thing? that would be bad juju. So when we think about the gas molecules we have, we are at a relatively high enough temperature from the universe pumping energy in here to keep them from losing their energy as they make the collisions and hit us. They hit us, they bounce back, they go off on their own way, and everyone's happy. And then gas molecules travel in straight lines. Now, this is a weird one to think about because either you're thinking, well, why wouldn't they? Or you're thinking, why do they have to? So, I could like do this. Show of hands, how many people think, duh, they have to be traveling in straight lines? We can use our show of hands thing. Ooh, look at that. Oh, we got some hands. I got one hand. All right. So one of you, how many people thought that it would be just traveling in weird squiggly things? Well, I should have asked that a little more succinctly because now I'm thinking like, oh, are you guys answering the first question or the second question? Oh, I can't expand it out like that. Is anybody gonna take the squiggly and just sort of say me? I will.
I say squiggly.
I say squiggly, yeah. You know, I would have thought like, well, heck, why do they have to travel in a straight line? Why can't they just sort of bounce around and do whatever they want? Well, there's a problem if they are doing whatever they want. If they're doing whatever they want, they're not behaving, right? So imagine even right now, you're talking, you're forcing air out of your lungs to go past your vocal cords so you can speak. It's going one direction, out your windpipe. What if one of those molecules decided to go the other way? That would be weird. It would also be weird. If you think about it, you have a bunch of nitrogen and a bunch of oxygen in this room right now that you're breathing in and out. What if all the oxygen molecules that were headed right for your face were like, yeah, I don't really feel like being consumed. How about I just suddenly go around you? What if they just decided, I don't feel like going towards you? That would be a bad day.
Yeah, we can breathe.
Right, right. Even if a bunch of nitrogens came in to fill their spot, you'd have a bad day. Imagine if the air around you itself just said, look, I don't want to touch you. All of the air molecules. And they just like opened up a big void around you. That'd be kind of weird. So even though it's perhaps an intuitive thing to say, it's a powerful thing to say because the ramifications are whatever direction that gas molecule is going, it will continue to go. And it does. Because if it had its own choice and did its own thing, it would not behave. We would not be able to model it. And the fact of the matter is we can and we do. Therefore, these molecules are going one direction. Of course, when they hit stuff, they can bounce off and go a different direction, but they're going to go off in a straight line. So there we have it. They're mostly empty space. They don't like each other or their container. They don't stick to anything. They hit, they give their force, they come right back and they don't lose energy and they travel in straight lines. This is how gases behave and this is why they are predictable for the quantities that we are going to be measuring, maybe even soon. Okay. Yeah, actually, let's talk about a little bit more of the intuitive stuff with just a touch of math, meaning I'm just going to rearrange something. So I'm going to go back to, let's do some more intuition with just a little math. Now this math won't be any numbers. I'm going to go to PV equals nRT. I'll define it again a little bit later, but suffice to say, you know, that P is pressure. V is volume. T is temperature. And N is moles, the amount. And then there's this guy R. This is called the gas constant. We'll talk more about this toward the end of the next lecture. But it's given the name gas constant because it is
Constant.
constant. Okay, so when we look at this, if we rearrange PV equals nRT, and we take it for R equals PV over NT, which means it is constant. This ratio right here is constant. What I want to do is talk about what is commonly called the individual gas laws, and I'm only going to do it qualitatively. We'll do the numbers next time. I want to look at the individual gas laws as they apply to the fact that when these people did the experiments, once they knew how to measure temperature and pressure and volume and all that stuff really well, they noticed that there was this constant value that kept popping up, and then they noticed that their cool little intuitive, oh yeah, I heat it up, it gets bigger, actually had a mathematical basis behind it. So what we're going to look at is Avogadro's law. What he's going to do is he's going to take a gas and he's going to keep the temperature and the pressure constant. Temperature and pressure constant. And so I just want to point out, if we have this PV over NT is equal to a constant, and if T and P are also constant, then I can actually move all of them over to the constant side. Move temperature and pressure to the constant side. So that's just a new constant. It doesn't matter. It's just a bigger constant. Then we'd have volume over number of moles is equal to a constant. Okay. Now that's the math behind it, but let's just talk about the physical behind it. Avogadro keeps temperature and pressure constant, a very easy thing for him to do. He does it in his lab, period. The pressure inside the lab is not going to change. The temperature is not going to change over the lifetime of this experiment. Those numbers are just a thing. He takes a balloon, he puts more gas into it. As the number of moles increases, as the amount gets bigger, will that balloon, drum roll please, get bigger or smaller?
Bigger.
Yeah, you put more stuff in it, it better get bigger. So as the number of moles increases, the volume has to increase as well. And actually the math over here in that V over N equals to constant, if that volume gets bigger, then N has to get bigger to maintain this number. But you know what? We don't have to actually use the math to do that. We can just do intuitive. So as the moles go bigger, the volume is bigger. And as the number of moles decreases, as you let stuff out of the balloon, the volume, of course, will go down. He keeps temperature and pressure constant. He looks at moles versus volume. And say, what is that relationship? Now, Avogadro was not done. He's also going to keep volume and temperature constant. Also keeps V and T constant. He's going to look at number of moles versus the pressure. Now, we already know intuitively what this is. As the number of moles gets bigger, as you take a sealed container, right? He can do this. He can have a hard metal container whose volume will not change. He'll do this experiment in his lab where the temperature is not going to change. And he's just going to push and push and push gases inside of that chamber. As more moles of gas, as more amount of gas gets shoved into that chamber, is the pressure going to go up or down?
That's it.
Yeah, look at this. And of course, as you take stuff out of there, as you pull a vacuum on it, the pressure will go down. Now, this right here is intuitive. By the way, if you solve that self-same equation above, you will end up with pressure over the number of moles is equal to a constant as well. Solving above. And mathematically, we can see that relationship. But we don't need the math right now to understand what these people saw, okay? Now, Avogadro loved the moles, so we like playing with the moles, but as soon as he started doing this, and hopefully you guys are being like, duh, well, you gotta take a step back. All of these duh moments that we might have where we go like, you know, of course you put more stuff in there, the balloon gets bigger, duh. So then why is it that this guy, this Mr. Avogadro, gets to be so high and mighty and put his name on a physical law that is unbreakable? It just is an observable thing, right? Remember, natural law versus theory. How come he gets to do this? Well, because he did the experiments, because he quantified it and proved that this law is immutable, as long as it's ideal. And so with Avogadro doing this sort of like duh moments and getting to put his name on stuff, some other people got, je ne sais quoi, jealous? Hey, did I do that right, Jordan? Did I do my je ne sais quoi?
Yes, that's correct.
All right. So basically, other scientists said, wait a second, if you're going to get your name on some laws by pointing out the obvious, how about I look at the obvious and prove it as well and put my name on it? And certainly other people did. So there's this guy named Boyle. So Boyle's law. This one is perhaps the least intuitive, but, and I wish I had my vacuum chamber to show you, but Boyle's law is going to keep a constant number of moles and temperature. It's going to look at pressure versus volume, okay? So as the pressure goes up, now keep in mind, I wish I could do this here. Imagine you have a balloon full of some gas and you suddenly increase the pressure inside of the room. Will that balloon get bigger or smaller as you pump the pressure into the room?
Smaller.
Smaller.
That's right. It's going to get smaller. It's going to get smaller, okay? And it's going to get smaller because you now have more force on the outside of the balloon than on the inside of the balloon. So as the pressure goes down, let's say we pull a vacuum on it, and this is what I would have been able to do in class, you'd watch that balloon get bigger. And we'll look at the actual numbers on this when we do problems. But suffice to say that basically this is what Boyle did. He did all the experiments, and he proved that these laws were immutable, and goes, ha, I have my name on one too. Take that, Avogadro. Now, we do know these as well, though. How many people here have started driving up to Lake Tahoe and you're sitting there napping, you grab yourself a whole bag of chips and you're mostly all the way up, and all of a sudden you're boom, coming from the back seat of the trunk or something like that.
That literally just happened to me driving to Louisiana.
Yeah, you're probably going over some pass or something, and your bag of chips exploded. If you think about that, we already knew this was going to happen. As you go higher up in elevations, the pressure drops. So all the gas molecules on the inside of the bag are like, woohoo, we can push back even harder now. And they do. And they push back enough that the bag of chips breaks. Now, when I was in college at Cal State Bakersfield, one of my teammates actually worked at the Frito-Lay chip plant, potato chip plant that was just outside of Bakersfield, and told me something that I thought was interesting, that depending on where they're shipping these potato chips, they will sometimes underinflate them. You know, they put a bunch of air inside of the chip bags, basically so you don't have a bunch of crushed chips by the time you get there. Give them enough room to run around, so when you stack them on top of each other, they don't break each other. That's why there's gases on the inside. But if they are going to take from Bakersfield and go up to like Denver or something like that, they will underinflate those bags so that by the time they get to Denver, they're the right size. That's kind of cool.
That is cool. My bag of gumbo actually burst open and went all in my ice chest. I was so mad.
Oh.
Yeah.
I would almost say that's bad juju. But it doesn't work. Bad gumbo, bad juju. Yeah, anyway. All right. All right, so Avogadro does one. Boyle does one. Someone else says, what about me? And then we have Charles' Law. Charles says, look, if you can do this, by the way, Boyle did this very easily, right? He can take a balloon, fill it up with in the laboratory where the room temperature is not going to change, and put some pressure and take some pressure off of it. Just to prove. Next. Charles says, hey, this has got to be another thing. He's going to keep a constant. Number of moles and pressure, and he's going to look at volume versus temperature. Again, this is another easy one. It's almost like, why didn't Avogadro just keep going and get all these out? And he could just be like, the entire thing is my law. I don't know, but other people beat him to the punch on these other ones here. So Charles' Law, he takes the number of moles of gas, keeps those constant. How? He just puts them in a balloon. Nothing goes in, nothing goes out. Ties it off, says, hey, I'm in my lab. Guess what? The pressure in my lab's not going to change. And what's he going to do? He's going to heat up that balloon and cool down that balloon. And we know what's going to happen here. We talked about it when we started. As the temperature increases, the volume increases, and vice versa. As the temperature goes down, the volume goes down. Think hot air balloon. Right? It gets big. If anybody here is from Napa and they went to that Festival of Lights things that we have every year, they usually get 2 or 3 hot air balloons to get down there in the commons area, and they start firing them up. They start getting the air inside of that balloon hotter and hotter and hotter, and that balloon gets bigger and bigger and bigger. We know this. We know this. Finally, we have Gay-Lussac. Unless I'm not saying that right. Frenchman, is that Guy or Guy?
It's Guy.
Guy.
Yes.
Lussac.
Yes, Guy Lussac.
Guy Lussac. Okay. He is going to keep a constant number of moles and the volume. And he's going to look at pressure versus temperature. This one's going to be easy. It's a sealed container. He just takes a jar or metal container, caps it off and says, look, I'm just gonna heat it up. We know what's gonna happen, guys, here. We know what's gonna happen. As the temperature increases, the pressure is gonna go up. And as the temperature drops, the pressure drops. Ooh, I could probably do this. Hold on a second. Hold the phone. Can I do this? Let's see. Hold on a second. I'm going to pause real quick. Resume. Cool. So I went ahead and I found something that I think is kind of fun. And this is, can you guys see the YouTube there?
Yeah.
Yeah, okay. So I'm at least get in theater mode. So this was actually a curious case. Down in Texas, in oil country, they have these tankers that they'll transport the oil to different refineries for being turned into gasoline and you name it. And so they have these big black cylinders. They fill them up with oil. They take them someplace. Well, eventually things get gummed up and you have to clean it out. The protocol is somebody in a bunny suit gets in there with a big steam cleaner and just starts basically power washing the inside. And they let it drain out the bottom. The other protocol is when you're done, do not close it up. Guess what they did?
They closed it.
Yeah, they closed it. And they closed it because it was a thunderstorm was going to start rolling in, which meant they just didn't want water to get in there. They just got through cleaning it. You know, they didn't want anything to get blown in and otherwise have to come out and re-clean it. So what they did is they closed the hatch. Now, they have just been steam cleaning this thing. This thing is ridiculously hot, right? They've got steam heating this thing up. They hop out, they close it up. This is now a sealed container. It is hot. The storm front rolls in, okay? The temperature drops tremendously. And as the temperature dropped, the pressure inside of that can also dropped. And they came back to find something very peculiar. Now, what they're doing right here in this video is actually artificially simulating what actually happened to this truck. And that is, they're like, there's no way that you can actually have the pressure decrease enough for this to occur, right? Well, guess what? And it is a catastrophic failure. In a normal class, I would actually do this with aluminum cans. I would essentially just get some boiling water in them, get them all hot and steam, and I would upend them into an ice bucket. And just the cooling of the aluminum on the outside would, where am I going here? Just the cooling of the aluminum on the outside would be enough to drop that pressure inside the aluminum can and crush the aluminum can. It's actually pretty darn cool. But there was a real life example of just your ideal gases at work doing their thing and doing exactly what you and I think that they should do. And that is, as the temperature dropped, the pressure inside of there dropped and the atmospheric pressure crushed it. Just crushed it. Okay, what I would encourage you guys to do, we're gonna stop here in just a second, is I have a set of notes on my webpage about a bunch of problems that we're going to be doing. I would highly recommend you take a look at those problems because I've done a lot of explanations in there and some problem solving. And what we're going to do when we come back on Monday, on Monday, is we are going to do just problem after problem after problem, basically trying to do any and all versions of these problems as we can, so that you have at least one example or more of each type of question that could be asked of you, such that next Wednesday, we'll just knock out a pretty easy exam and call it a day. So I really encourage you guys to look at those because I will be using those as a reference and I'll probably just make some up on the side. which would mean that I think I'm going to go ahead with Martucci. I want you to be on the calculator for me so that you can get some stuff. Nathan, you as well. Just so that if I make up new numbers, we can get the new values, because I hate using examples we've already seen. We might as well just have the ones from my webpage as secondaries, and let's make up our own problems as we go.
You got it.
Forrest, where are, I'm on your Concur, I don't see them.
I'm not on Confer. My actual webpage, yes, thank you. I will try to see if I can suck them off of my actual webpage and put them on Canvas, but if not,
What's
go
your
to my actual webpage, and if I swear, if somebody in the chat room goes like, how do we get to your webpage? Do you know how to Google? I'm the first link. So go to Google, type in my name. It'll pull up my Napa Valley page. You'll see a Chem 110, and there'll be some ideal gas notes there. The typed up ones might have an error in them. I forget where it is, but I know there's one, and I've never fixed it because I can never find the original file. And I really don't want to take the time to go retype that whole thing again, because it took me like 2 hours to do it. So if you run across something that looks a little weird, just put it in your back pocket and ask me about it later. I can fix it for you. The written ones are all good. How do we get to April? Oh my gosh.
I see it.
You or Reagan, I was gonna have to.
No, I knew you were thinking. I have it. I'll put the link up right now.
Oh, look. April, oh, that's so funny. Oh my God.
I just did it because you said, if I can be busy.
I know. That's why I was laughing. Okay, so that's it for the notes here. The one thing I do want to say, by the way, I've been getting a few questions about this, so I'm just going to go ahead and say it now. That exam 4 that we took, I'm throwing it out.
What? Yes.
Thank you.
Yes.
So there were.
4, not 5?
Wait, you mean 5 or 4?
No, the one with all the nomenclature stuff.
Oh.
Oh,
Never mind then.
no.
Never mind. I take back my woohoo.
Yeah, me too.
No.
But yeah, there were quite a few anomalies, and too many that I could ignore, and so I've decided to throw that test out because of those.
Oh.
So, so I just want to put that out there. So for those who are like, "Oh, are you sure you got my test?" Yeah, I got it. But I'm throwing it out.
Oh.
So, all right, I'm going to go ahead and stop the recording.
So since we were talking about